Alright, in this video we're going to talk about how to prove some statements about parallelograms. In each of these you're going to be given at least one parallelogram and you're going to be asked to prove something about it. Now anytime you deal with parallelograms, you naturally involve parallel lines, which means the angles that we've previously talked about with parallel lines, alternate interior, alternate exterior, and so forth, that you see here on the screen, that those may come back. They don't come back into every proof, but it is a possibility. So for example, you may see corresponding angles. Remember, that would be like angles 1 and 5, angles that are in the same position. Alternate interior angles, angles that are between the two lines, interior, but on opposite sides of the transversal. So maybe angles 3 and 6 or 4 and 5. Alternate exterior angles, outside the two lines on opposite sides of the transversal. One example there would be angles 1 and 8. And then lastly we have the consecutive interiors. And consecutive interiors work differently in that they are not congruent, they are supplementary. Our pair of consecutive interior angles in this case would be angles 3 and 5 or 4 and 6. Now, more commonly, not to say it's every time, but more commonly you'll see that it's going to be the congruent parts that you end up using. And you'll kind of see that come into the proofs we're going to do in a little bit. Another thing you need to be aware of that sometimes happen with congruent, or I'm sorry, proving parallelogram things about them, is that with parallelograms we have to keep in mind, obviously, the properties of a parallelogram. And we've got these 5 listed here. We know the opposite sides must be parallel, that both pair of opposite sides must be congruent, that both opposite angles must be congruent, the diagonals bisect each other, and then lastly the consecutive angles are all supplementary. So those are things that there again may be useful in a proof, but not necessarily in every proof. The last thing you need to kind of review is congruent triangles. Congruent triangles don't have a large presence in parallelogram proofs, but as you go through worksheets and textbook problems and so forth, you'll find that they do occasionally come up. So if you're proving that two triangles are congruent, recall that your methods of proving two triangles congruent would be side, 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 angle, 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 side, and hypotenuse, leg. We'll look at an example of that later. If you're trying to, or if you're told to, triangles are congruent, then you want to use CP/CTC, which means you want to look for parts of those triangles that are useful in proving whatever it is you're trying to prove about your parallelogram. That typically comes in when you're trying to prove that a quadrilateral is a parallelogram, which is in the next set of proofs that we'll be looking at. So for now, each of these proofs that we'll be dealing with today will have a parallelogram, at least one of them, given, and you'll have to prove something about it, or based on the diagram. In this case, we're looking at ABCD is a parallelogram, and we're trying to prove something about angle 2 and angle 4. First thing I notice in the diagram is that angles 2 and 4 are not inside the parallelogram. They're not opposite angles. They're not consecutive angles. They're most definitely not diagonals, and they're not sides. So none of those things that are properties of parallelograms are going to be useful in this proof. What I do know, though, is that because ABCD is a parallelogram, that means it must have parallel sides. Sheer definition of a parallelogram. With parallel sides come those angles we just talked about momentarily. The alternate interiors, the alternate exteriors, and so forth. So in this case, where the angles we're trying to prove something about are not interior angles in that parallelogram, that's where I want to use those angle pairs that we talked about in a previous chapter. So we start by setting up our proof with our given. ABCD is a parallelogram, and that would be given. Now, you may or may not recall that when dealing with the alternate interior angles theorem or any of those other postulates and theorems, they start off with if two parallel lines are cut by a transversal. In this case, although it's understood, it has not been explicitly stated that the lines are parallel. We're told that ABCD is a parallelogram, which we understand to mean the opposite lines are parallel. But it needs to be stated within the proof before we can use the alternate interior, alternate exterior, corresponding, etc. So your second step, whenever you want to use those theorems, is to state which lines are parallel. In this case, line AB across the top is parallel to line DC. And on the left side, line AD is parallel to line BC on the right. And that's just simply by the definition of a parallelogram. Those lines need to be stated parallel anytime you intend to use alternate interior angles, alternate exterior angles, consecutive interior, or corresponding. You have to have stated the lines are parallel first. Now we go to the diagram. And I'm looking to see what types of angle pairs do I see present in the diagram itself. First thing I notice, angle 2 and angle 3 are alternate interiors, which makes them congruent. So angle 2 is congruent to angle 3 by the alternate interior angles theorem. Likewise, looking at the diagram, I see a pair of corresponding angles, angle 3 and angle 4. And I know from the corresponding angles postulate that those must be congruent as well. So angle 3 is congruent to angle 4, corresponding angles postulate. I have a tendency to abbreviate things more for the sake of time than anything else. And what I see at this point is that I have two congruent statements, both of which involve angle 3. When that happens, when two angles are congruent to the same angle, the transitive property allows us to conclude that they must be congruent to each other. So in this case, for step 5, the transitive property makes angle 2 congruent to angle 4. And that takes care of that proof. So I looked first at the diagram to determine if the angles I was going to prove something about were parts of the parallelogram. In this case, they were not, which led me into those parallel lines that we previously talked about. In the second proof, you're going to see a slightly different situation. Here we're given two parallelograms, ABCD and AEFG. And looking at the diagram, we can see that the numbered angles 1, 2, and 3 are, in fact, interior angles of those parallelograms. Specifically, as we look at parallelogram ABCD, we can see that angle 1 and angle 2 are a pair of opposite angles in that parallelogram, which makes them congruent by that theorem about parallelograms. Likewise, if I look at the second parallelogram, AEFG, we can see that angle 2 and angle 3 are again opposite angles in a parallelogram, which would make them congruent. So let's write down what we've already discovered. Start with our given. So the first thing you want to do in these proofs is look to see, especially if it deals with angles, are the angles inside the parallelograms? And if they are, which of those properties of parallelograms may be useful? If they're not, go back to those parallel lines. Okay, so we said in the pink parallelogram ABCD that angle 1 was congruent to angle 2 because the opposite angles of a parallelogram are congruent. Looking at the second parallelogram, AEFG, the one that we outlined in green, we had another pair of opposite angles. in this case angles 2 and angle 3. Because it involves the same reason, we can put them in the same statement. If they had different reasons, you would need to separate it. Now at this point you should see two congruence statements, both of which involve the same angle, angle 2. So that same transitive property that we applied in the last proof will be useful here as well to make angle 1 congruent to angle 3. Specifically, this would be the transitive property of angle congruence. And that takes care of that proof.